we're going to look at what magnetic fields do. And we'll start by using this device right here. This is an old school television, and it fires an electron beam from the back to the front, hits the screen. We've surgically altered it so it just makes a line on the front of the screen. So it comes out of the back, spreads out, makes a line. I'm going to take a magnet and bring it up next to the screen. Now here's the north pole of the magnet. So the magnetic field is going in this direction. The electrons are going in this direction. And which way do they move? Answer, they move down. So notice this. Magnetic field this way, electrons this way, force that way. The force and the field and the velocity are all perpendicular to each other. And that's one of the hallmarks of the force that magnetic fields exert on moving charged particles. You have these mutually perpendicular vectors. And we have a description of that in the book. Now, another thing we have to think about is how you determine the direction. Because think about this. Velocity is going this way. The field is going this way, and the particles move down. But another possibility is the particles could move up. They could be deflected up, okay? So how do we know that it's down and not up? We have something called the right-hand rule. And the right-hand rule is a set of three vectors which are mutually perpendicular. One of them is in the direction of the velocity, one of them is in the direction of the field, the third one is in the direction of the force, okay? And we have an illustration in the book that shows you how to use your fingers to implement the right-hand rule. You have the velocity and the field and the force, and they're mutually perpendicular. But this little device that I have right here is another way to implement the right-hand rule. Velocity is green vectors, field is a blue vector, the force is a red vector, and they're oriented like so. Now, think about this. I have the north magnetic pole that comes in, and the beam goes down, and so the force is down. So the velocity is this way, the field is that way. The right-hand rule predicts a force that goes up. Why, in fact, does the beam go down? Something is up here, and what is it? We'll give you some choices. And of course, what's up is this. The electrons are negatively charged. The right-hand rule refers to the force on positively charged particles. For a negatively charged particle, it's in the opposite direction. So velocity this way, field that way, predicts a force upward, but for negative charged particles, the force is down. Okay, we have another question for you. Suppose, instead of bringing in the north pole of the magnet, I brought in the south pole. If I bring in a south pole of a magnet, how will that deflect the beam? We'll give you some choices. Well, if I bring in a south pole, the field goes into the south pole. Instead of going this way, it comes this way. The right-hand rule says for a field in this direction, for a velocity towards the screen, I would predict a force that's down, but since they're negatively charged particles, they will go up. And so, in fact, that is what we see. The beam is deflected up. The beam is deflected up. Now, moving beams of charged particles is important, and we'll look at examples of this in the chapter that are extremely important. But what's more practical on a day-to-day basis is this. Magnetic fields exert forces on currents, because a current in a wire is just moving charged particles. We'll show you a couple examples of this. Now, right here, I have a wire that carries a current, and it carries it from this terminal to this terminal. When I turn it on, there will be a current going in this direction. There's a magnet on the table. That's a north pole of a magnet. So there's a magnetic field which goes out. It goes upwards out of the magnet. Current is going in this direction. Field is going in this direction. When I put on a current, this wire is going to move. And think about this. Which direction will it move? It could move up. It could move down. It could move toward the camera, or it could move away from the camera. Which way will it move? And to be able to figure this out, you want to use the right-hand rule. So think about that. The current is going in this direction. The field is going in this direction. Which way will the wire move when we turn on the current? We'll give you some choices. Well, the right-hand rule says this. The direction of the flow of the current is just the direction of the motion of positively charged particles. So that's our velocity. The field comes out of the north pole of a magnet, so it goes up. So the right-hand rule predicts that the force will be away from the camera. So if I turn on the power supply, there's a current in the wire. Watch the deflection of the wire. And it is, in fact, away from the camera. Exactly as we predicted. Next question. How about if I was to take the magnet and flip it over so that we have a south pole? In this case, what will be the direction of deflection of the wire? We'll give you some choices. Well, in this case, the magnetic field is going down into the south pole. The velocity is still this way through the wire. And so we would predict a force and therefore a deflection that is toward the camera. And if we turn on the power supply, what we see is a deflection of the wire toward the camera, exactly as predicted. Now, I'll show you one other demonstration and talk about something that magnetic fields do. What magnetic fields do is they magnetize magnetic materials. And that's the topic that finishes the chapter. So I have a very strong magnetic field above this magnet. And so if I bring a bolt in here next to it, this bolt will magnetize with the south pole on the bottom and a north pole on the top. And so the bolt becomes magnetic. If I bring in a second bolt, it will magnetize. There were little magnetic moments inside this bolt that will line themselves up with the prevailing field, and so I'll end up with a south pole on the bottom and a north pole on the top. And if I bring in the two bolts next to each other, they're both magnetized, and they stick to each other. They don't stick to the magnets, but they do stick to each other. Now they're magnetized. And what makes them become magnetic is the presence of the strong magnetic field from this big magnet here. Because if I take this big magnet away, what happens is this. They cease being magnetic. They're magnetic when they're close to it, when they're in the presence of its field. But if I move them away from its field, they cease being magnetic, and they won't hold together. Now you can see there's a connection between electricity and magnetism because we've seen that a magnetic field exerts a force on an electric current. We'll consider this connection between magnetism and electricity much more in the next chapter.